lazy lists and non-lazy lists, and what's the difference? When I say lazy list, I'm not talking about the way you stand next to the water cooler. I'm talking about lists that do things just in time. So what I'm going to do is look at Linq queries and how they react to certain scenarios, and how there are a few little pitfalls along the way, some things you can't do, some things that are really useful, and some things that do not necessarily what you expect them to do. First thing I'm going to look at is a lazy list, and we're going to use the prime factors code that we did in the last couple of videos, and show how we can use that in a lazy list as just an example, and show what that actually does.
So what I've got here is a huge range of integers that I'm going to use the select extension to get the prime factors of each element. When you run this, you end up with an unresolved enumerable, so there's not actually any work being done. We can prove that it doesn't do any work by putting a breakpoint in the prime factors and rerunning this test in debug, and we'll see that the breakpoint inside the prime factors doesn't get hit. Now I'm going to force it to resolve the enumerable by using the toArray extension. Also note, I'm only asking for the very last element in that enumerable. It now hits the breakpoint in the prime factors. It only hits that breakpoint once. So in this case, it's lazy. We can see it's returned a single element, and this element is another unresolved enumerable, which is our prime factors. In the previous case, it was a lazy enumerable, but are all enumerables lazy? So we can force that enumerable to resolve by adding toArray. If we then debug this again, we can now see this is resolved to a single element array with another array inside containing the prime factors we asked it to calculate. So is that inner enumerable actually lazy? And we can show that by removing the toArray so it doesn't automatically resolve it, and add some breakpoints to the inner workings of the prime factors functions. We debug this as before. You can now see that it hits the breakpoints we've added. This shows that the second enumerable for the prime factors is not lazy. Now look at what happens if we try to resolve this huge enumerable of integers. So by adding toArray just after the definition of the enumerable, we'll force it to resolve. If we debug this and step into, or attempt to step into, we get an out of memory exception. So there's no way to resolve an enumerable of that size. Ah, well what about lists, I hear you say? Well, let's try. Let's try and resolve this to a list. So do the same thing. As soon as we step into it, we get an out of memory exception. So if it's lazy, does it do any work if we try and resolve it straight after the select? Well, if we run this, you'll see that it comes up with an out of memory exception in exactly the same way, because it allocates, or tries to allocate, the memory up front. This means that it fails fast, fails early.
A common pitfall is multiple enumeration.
If we do an enumeration twice on the enumerable, so we're going to do a for each over the last two elements, and then take the last single element and resolve that to an array. So as we debug this, we've stepped over the take two, so that's already taken those two elements. If we put a breakpoint, you'll see that it goes and calculates the prime factors of the last element again.
which a lot of people think, just running the same bit of code twice. What possible harm could that do? Well, I'm going to show you a little example that shows there's potential for some damage or some odd behaviour.
If you iterate over the enumerable multiple times with a function that multiplies the integer in the enumerable by the current milliseconds, it runs each of those and runs the function every time, but the result from the first iteration is completely different to the second.
One of the pitfalls with these lazy lists is that you can get caught out by mutation if you don't understand exactly what could go wrong. I'm going to do a small example here of how mutation can affect the results.
Given this relatively simple example, we've got a list that's instantiated with the numbers from 1 to 99, a middle select statement that just selects all the integers in that original list, and then an assertion that the last number in that list is 99. We can break this very simply by removing the toList here. This now means that the select isn't resolved, i.e. middle, until the final assert. Because we've mutated promise before that select's been resolved, it means that the last figure in that enumerable is now 33, not 99. If you consider what this might do in a multi-threaded environment, it could result in some quite unexpected behaviour. Just want to give a little shout out to the place where I started, because on the 1st of December this year, 2021, the humble BBC Micro will have reached its 40th birthday.